So the next talk is going to be by Satoshi Minamoto from NIMS in Japan.
Thank you. Thank you very much. Good morning, everyone, but good evening in Japan. So my name is Minamoto from NIMS NIMS Japan. So today I'd like to talk about our system development and system development for the structural materials. And so we are thinking to utilize the data from the system by using the APIs. So I'd like to talk about the national project. And this is very short story about NIMS NIMS, National Institute for Material Science, which is located just above 6 kilometers away from Tokyo Station. And the people, the number of people, researchers almost 400, and engineers almost 700, and totally 1,600 people are working on 3 locations in Tsukuba area. And one of the main our research work is to develop the database, and some of them are disclosed openly, freely on the web. So as a MatNavi application, and for example, the polymer databases or crystal structure databases, or this is maybe the phase diagram databases, and this is electronic structure databases or something. Of course, we can disclose the experimental data, just like a CCT databases, or for example, the superconductivity database or something like that. So today, I'd like to talk about what the materials integration is, which is developed in Japanese national project. And as you know, maybe you know about the ICME in the US or MGI in the US. ICME is the short for the integrated computational materials engineering or something like that. Materials integration in Japan is the concept of materials integration is almost similar to the ICME concept, which is very focusing on developing, reducing time of developing the structural materials. Okay. In the concept of materials integration, we use this 4 scientific paradigm, just like experimental and theory and numerical calculation and data science, in order to understand the linkage of the processing and structure and property and performances. And finally, we are focusing on the tackle to the inverse problem, which is very important to design the structural materials. That is, if we want to the best, for example, the strong materials, so what the composition is like. So such kind of problem is our focusing on. Okay. And actually, our project is in the second phase. The second phase has just started 2018 and will finish in 2022. And first stage is before 5 years. That is 2014 to 2018 or so. And almost over the 100 researchers are participating to the national project in order to establish the procedure to design the airplane material, for example, the wings or engine turbine or something like that. So we have 3 domains, A and B and C. A is focusing on the system development, and analyze for the metal problem. For example, the 3D additive manufacturing or something like that. So we are focusing on establish very fundamental technique in the A domain. And she and B and C is focusing on the FAIR-D and the 3D additive manufacturing application, respectively. And however, the more than 100 researchers are participating in the whole project. However, the 3 or 4 person for the system development, and I am the responsibility of the system development. And the budget is $220 million US, or almost $20 million US a year, and yes. And here is the R&D concept for inverse problem analysis for our second stage SIP project. And of course, we need to design the very accurate forward problems design as a workflow. Okay, in this picture, so we can, for example, we know about the compositions of the alloys, and of course, we know the temperature of the treatment, so we can understand the microstructure evolution based on the, for example, the Carport calculation or phase field calculation or something like that, as a forward programs analysis. And after we capture the features of microstructures, we can move to the analyze to the for example, property analysis or performance analysis. So for example, the chemical composition or heat treatment condition is the process in the PSPP relations. Okay, and this is the microstructure of the alloy, is the structure data, structure section of the PSPP relation. And finally, for example, the SS curve or tensile strength or fatigue life limit or creep lifetime or something like that is the property. And performance will be the most emergible features based on its boundary condition or environmental condition or something like that. So ordinarily, so we analyze PS property, P problem in the forward analysis. And so once we got the workflow from this direction, so we can move to the backward as a inverse analysis. But sometimes we need another technique to handle the very few data, other sparse modeling data or Bayesian analysis or something like that. Okay, and this is just an example of the our system. Here we call MINT system. MINT system is short for the materials integration by networking technology. So hereafter, so I will call our system as MINT system. And in the first stage of our project during this time, so we developed a web-based application to design the workflow of the analysis, forward analysis of the structural materials. And of course, we can we need the player how handle the design the workflow. So we developed a workflow player, and of course after that, so as a post treatment, so data bureau or something like that has been developed in the first stage of the of our project. And yes, and here is just an example of the simple workflow. And the red, blue icon means the input, and the orange and yellow icon is the prediction model. In other words, the physical model. And the gray icon means the output parameter. Okay, so to manage the this workflow, of course, the numerical input parameter or output parameter is essential. However, we need the background data as a metadata we correct. Okay, so the vocabulary inventory system and the calculation data are stored in our system. And the below picture is just a very simple example of a workflow in order to estimate the fatigue life limit. And in the workflow, about 1, 2, 3, 4, 6 or 7 prediction modules performed automatically in the system, and the user input to something and they get output, output. So our workflow management system consists by the 3 parts. One is design part, and one is vocabulary management system, and the other is database of experimental data or calculation data. Okay, so it is very important to describe the data flow of the structural material forward problem in order to understand the PSPP linkage. Okay, and each prediction module passes data and the physical background and the materials engineering information as a metadata and physical, for example, the calculation condition or experimental condition or some other restriction in the materials. Okay, so this kind of information will be very useful to generate the machine learning models as reusable prediction models in the system. So it is very important to reuse those models in the system. Okay. And here's our data, how the data is stored in the databases. And blue is input port, and the yellow one is a prediction model, and the gray one is output port. And of course, the data input file, for example, for the phase field model or FM model or something, is important. However, it is difficult to make machine learning models by the input file itself. So we have to divide the language of material science of engineering before storing data. Okay, so we make it possible to extract the parameters as supervised data for machine learning. So very important section here. And of course, the prediction model has very various types of metadata. So we need to store as much as possible. However, descriptors are expressed in different ways by different people and need to be standardized. I mean, the here or here, how to express the, for example, the test stress or tensile stress or applied stress or something is different by the people. So we don't unify the expression of the input to output ports. So we cover to absorb the difference by the making the API, database APIs. So that I'd like to talk about later. And here is the graph structure of the database of our workflow system. Okay, input port and output port and the predict input port and output port and the prediction model and the relation between each nodes are expressed as expressed just like here. Okay, and of course the attribution of a PSPP or something, for example, the tag or PSPP or some other attribution is applied to the port information. After that, so we can connect, merge all of the workflow data stored in our system. Okay, and here is the accumulated workflow information as a graph structure databases. And yes, we can store the many different workloads by different researchers. But we can merge it as a one graph or several part graph are still existing, but we can get the very, very big graph of the our workflow system. This means each workload, part of the graph are developed by the one people. However, we can search passes from, for example, here to here by passing, for example, this route or this route or this route. So our workflow system, I believe, our workflow system can merge the wisdom of the very, very different people in the community. Okay, and this is just like an example of the how to build the workflow from existing prediction modules. Okay, and this is very complicated, and I will show the video based on the Japanese language. I'm sorry, so but I can express, I can explain as much possible. I'm sorry. And once we can, once one people build the workload here, and another workload here, another workload here, we can, for example, connect workloads if the input 3 port and output 2 port, the information is matched. Okay, at this time, so we assign the persistent ID for each port. So we check the ID, and so if the ID matches, so we can connect the workflow each other. And this is we call the suggesting feature in the workflow. So in this case, the thermal conductivity analysis and the brittle distinguish the brittle. Yes, I'm sorry. And but so we don't have any workflows because the very, very far from the very long distance between descriptors from the start point and end point. And if the models are stored in the system separately, so our system can suggest the workflow as a candidate workflow. So of course the users have to check the suggested workflow is variable or not. However, the system can understand. I'm sorry. So the user can understand the very, very small workflows, and the system can connect by judging the persistent ID matching conditions. I'm sorry, I can't explain so well. So, but if the user know about very small information about the behavior of the material, for example, the composition and the displacement or something, but if the modules are stored in the system can judge the match of the ID, and if the system can find the usable workflow, so system can suggest to the users and connect and build the workflow as an proposal. And it's also the API is very important, we think. So at the first stage, our system version 1 is established on the 3 years ago, 4 years ago. So we are now developing APIs to handle the features of our system. At this moment, so we have developed very, very various APIs in order to handle our system features. So by making an API, so user can make their own GUI-based application, because sometimes it is difficult to use our system if the user is not familiar to the computer system or something like that. So we need to establish the environment to make the GUI application very easily. Okay, and here's the workflow to analyze the weld fatigue analyze for the weld joint part. But sometimes user cannot use as is. So we developed our own web-based GUI system, and we applied, for example, the inverse problem as an optimization of the parameters of the heat input condition, or for example, the distance between here, or distance between here, or something like that. So user can easily use our inverse problem analysis environment. Okay, and after that, so we are making data of structure, because sometimes basically for the structural materials, we can get the data described as a relation of process and property. For example, chemical condition and temperature, and for example, the strength of the material, something like that. And sometimes we cannot get the structure information, just like, for example, the micrograph picture, or some dynamical information of that. So in order to understand the relation of PSPP, so we need the structured data. But existing data does not have such kind of data. So what we are doing is to generate its structured data by the numerical calculation or simulation technique or something like that. So after that, so reusing the system is very important. So models, I mean the prediction models, or based on the physical models or machine learning models or something like that, can be shown as an alternative tools in our MINT system. If the physical model is replaced by the machine learning model, so the calculation time will be dramatically reduced. So it means increasing parameter search speed with surrogate models. So after that, so user can switch to the detailed model, FEM or first principles model or something like that. And here's our concept to generate the structured data. And the top of the figure is the conventional databases. I mean, the process property linkage is described in the databases. But we need the structured data in order to understand the PSPP relations. So in order to understand, so we need mesoscale analysis technique, just like some dynamic calculation or first principle calculation, or deferred data storing such kind of data. And or merging database is very important. So today I will talk about A and B. A is the how to manage the several databases described in different language, different terms. And B is the data search and for the first principle calculation or databases. And here's the schematic picture of the aggregating many databases consist of a small number of data. Data B, database 1, database 2, 3, 4 we are having. but described in very different way. The schema is different, item name is different, metadata is different, or unit is different. So we are tackling by using absorb this kind of inconsistencies by using APIs or conventional dictionaries or graph databases, or by using the QUDT developed by NASA. So we can adjust, arrange the same structure, for example, data B or database 4 and DB, and we can extract the data as one in one picture. And here's the one example about the relation between the yield stress and tensor strength. One is from 5 databases. Okay. And after that, we can filter or omit data in order to perform the machine learning technique. And the structured data is very important. And here's just, of course, just an example how to import the S information, structure information in the machine learning models. And this is the building CCT data, continuous Turing transformation data, which is very important in the steel development in order to understand the microstructure or phase transition temperatures and something like that. In our institution, so we have several hundreds of CCT data. So we can, of course, build the prediction model of the CCT data by using the composition or cooling temperature, cooling speed or something like that. However, in this calculation of the Gauss-Olson model, which is using the some dynamical driving force, something like that, driving force information of from the Gauss-Olson model is incorporated in our model, for example.
Minamoto-san, you should really start concluding because we are approaching the end of the time that is allocated to you.
Okay, I'm sorry. I will finish in several slides. Here's the example how to handle the first principle data in order to calculate the some dynamically stable calculation. Okay, and thank you very much. So we have developed the Mint GUI, which is performing direct problems for the structural materials, and the API will be used in order to understand the impulse problem or optimization by using the PSPP relation. Thank you very much.
Thank you. We have time maybe for one quick question because we have here a coffee break and we have to start.
I'm sorry.
No problem, no problem. Maybe a quick one from me. So, I mean, in terms of, compared to what was discussed in the previous talk, in terms of collecting the data, the experimental data, so do you have tools that you have developed yourself also in connection with that?
You mean the connection between experimental and the calculation? Yes, we developed our own. Yeah.
Okay. Are you sharing that, or is it something that it's private?
So I'm sorry, this is very Japanese across the project. So I will ask to our bosses to.
No,
share,
it's just to know. It's just to know.
Yeah. Okay. So I will let you know later. Yeah.
Okay. There's a question by Ralph. Yes, Ralph.
So I have a question to kind of which level of properties you envision to be able to treat, and particular also if we think of device functionality, then the functionality or the property of a device is not only the property of a single material, but arises from combining specific materials together to achieve a new property. So do you foresee that sort of with your approach you can deal with this sort of more complex level of material properties, device properties?
Yes, we are discussing that. However, at this moment, so as you know, the data of structural material is very sparse. So we cannot use such kind of detailed meta information or detailed the properties. So in this situation, so we use this very conventional property. However, yeah, if we can get much more data about the device data or some other data, so we can maybe find out or distinguish the differences between the properties. At this moment, we don't.
Okay, thank you.
Okay, thank you very much. So we're going to stop here for our coffee break, and so we'll reconvene at 11:15 as originally planned. Thank you very much.